So students, the next on the module 2 is about the another type of loading, that is half sine impulse loading. Half sine impulse loading. So here you can see this is the half sine loading. P0 sine omega dash t. Why we are changing this? Because it is not natural. That is why instead of omega dash. So here it is again. You can see here there are two phases. Up to this t is equal to 0, one phase is there, then greater than t. So here it is t less than or equal to t0. This is the phase 1. Here t greater than t0. In phase 1 load is there, phase 2 load is not there. Now here again I am taking the first undamped vibration stage. So my equation, I will be having two conditions. So phase 1 it will be the mx double dot plus kx plus kx is equal to p0 sine dash t omega dash t, then it is equal to 0. Now again the first solution I am taking, that is x1 first phase solution. It is of two stages. One is complementary part and other it is the particulate integral. Now what is complementary part? Now here since no damping is there, it will be x1 a cos omega t plus b sin omega t. X1 it is equal to c. Now x1 pt will be c sin omega t. Okay. Now here I can find out what is the equation. So this same we have studied in the harmonic there. Harmonic load we have studied. You should remember this equation. That is x1 pt will be getting as p0 by k into 1 minus beta square sin omega t. So this we have already derived. Same derivation only. Next one we know that at x1 pt is equal to so this one will be your x1. Now I need to find out a and b. Okay, this will be my total solution. I need to find out a and b. For that my boundary condition is this one. At a t is equal to 0, that is my initial condition. So from both initial conditions I can find out what is a and b. So this will be my solution, first phase solution. Now in the second phase, what is the condition here? Only x2, here only complementary, no particular particular solution will be there, only complementary solution will be there. So I am just writing, so this will be equal to x2 ct. There is no x2 pt. X2 pt, this term is 0 because there is no force. So t will become t minus t0. Again, how we are finding out? Here the boundary condition is changed. What is the condition? Initial condition is t is equal to t0. x1 is equal to x2 and x1 dot is equal to x2 dot. So I need to find consider both the equations, x1 this equation and this equation, and taking the derivatives I can find out what is a and b. So by finding what is a and b, by substitution I will be getting my final equation x2. Okay. So the same procedure is being followed. Okay, everywhere the same procedure. But you need to understand here, so many terms are increasing. That is a condition. Now again in the damped condition, you can see mx double dot plus cx dot plus kx is equal to p0 sin omega t. This is a damped condition. So our the phase 1 solution, here I will be getting another new term, e raised to minus omega t. Then it will be c1 sin omega t plus c2 cos omega t, because there are damping is there. So I need to find out by solving. This is as same as in the harmonic loading slide. You can just refer that slide. I can find out c1 and c2. Then applying the boundary condition, I can find x2 ct. The similar way I can find out. So this will be my loading. So from here I can find out the constants a and b. That is here I will be applying this. This can be added to. So the total solution will be like this. x1 is equal to x1 ct plus x1 pt. So here x1 pt we have found out. Now x1 ct, what is x1 ct? x1 ct is written here. It is this one. So by adding c1 c2, first we have to find out. Then we will be adding to this. Then we can find out by applying the boundary condition. I can find out a and b. Okay. Now similarly by applying the initial conditions, then second stage, one more phase is there. That phase also by applying the boundary condition, boundary conditions I can find out. Initial conditions I can find out x1 p and q. Okay. So this I am not explaining too much because it is just substituting and finding out the values. Now let's just look into a simple problem. So here in this problem, the mass is given, K is given. It is subjected to a half sine load as shown in the figure. Then find the expressions of the displacement of the system for t is less than 0.3 and greater than 0.3. That is both the phases. And what is the displacement at t is equal to 0.3? At here, what will be the displacement? So I need to derive the equations. So again, you can see this is my equations. For phase 1, the equation will be like this. This derivation you need to understand this equation. Then by substituting the values, here k is given, p given, then I can find omega. So likewise I can find what is the expression. Then for t greater than 0.3, this is my equation. So I need to find out x2 also. Then the displacement at x is equal to 0.3. So to find out the displacement at x is equal to 0.3, here at x is equal to 0.3. So x is equal to 0.3 means it will be this stage. So it will be the phase 1 stage only. Therefore, I need to substitute here. In this equation, I am substituting t is equal to 0.3. P0 and k are given, but beta it is not given. If it is given in question, you can just substitute that. But since it is not given, you can find the response displacement in terms of beta. That is not problem. Okay. So likewise, we can find out what is the answer for the displacement at t is equal to 0.3. And if omega or omega dash is also if it was given, we can find out what is the values. So likewise, you can find out the displacement for the single degree of freedom system. So basically, one thing I need you to understand is that this is the condition. So there will be two sets of conditions at t less than or equal to t0 and t greater. Both these conditions we need to find out the solutions. So that will be our total solution. Okay. So the next topic on this one second module is on vibration isolation. So that is a very important concept that you need to understand when you are practicing as an engineer also. What is isolation? Vibration isolation means the way in which I can isolate a building or a structure or a machinery from excessive vibration of the ground. What will happen if vibration, if a building is buildings are being mounted on the earth surface, and if the earth surface is vibrating, and if there is no mechanism to reduce the vibration that is being passed to the building, it will result in the destruction. So I need to isolate the building from the ground where the vibration is possible to happen. So that is the concept of this vibration isolation. So everything in life is in vibration according to Albert Einstein. So vibrations are produced by machines having unbalanced forces or masses. These vibrations are transmitted to the foundation upon which the machines are mounted. Hence it is essential to isolate the machines from the foundation so that the adjoining structure is not subject to heavy vibration. This is known as vibration isolation. So the main objective of isolation is to protect the delicate machinery from excessive vibration, and also to prevent the vibratory forces generated by the machine from being transmitted to the supporting structure. That is, there are two objectives. What is, for example, if I am having a structure like this, okay, it is supported on the ground. So sometimes the supporting structure can move and the vibration can be passed. So to reduce that, or this structure will be moving due to some loading or due to some vibrating instruments. So again, this type of vibration, it will be passing vibration to the supporting structure also. So both these have to be reduced. The efficiency of an isolation may be defined as the in terms of force, or no, the isolation can be of two types. That is force isolation and displacement isolation. That is, either the force transferred can be reduced or the displacement transferred can be reduced. Vibrational isolation may be obtained by placing isolation. Isolation mean refers to the reduced interaction between the structure and the ground. When a seismic isolator is located under the structure, it is known as base isolation. Base isolation is a very important term. That is, when a seismic isolator is that I will be showing the picture soon. Now, what is base isolation? Base isolation means the concept of base isolation is explained through an example of a building resting on a frictionless rollers. Now, you can see a building like this. So, initially the building will be, there are no rollers, you just consider. Then what will happen? If the support motion, this earthquake is happening, all the vibrating forces will be transferred. But if some roller like arrangement is there, then what will happen? Even the support is moving, the rollers will be adjusting, it will be moving. So, the vibration will be very less. So, we can protect the building. So, this is a basic hypothetical building and an example. Instead of rollers, we are using many other mechanisms are there. So, here you can see, so the basic concept of isolation is explained through an example building. So, when the ground shakes, the roller freely rolls, but the building above it does not move. Thus, no force is transferred to the building due to the shaking of the ground. So, simply the building does not experience the earthquake. That is one thing. Now, if the same building is resting on a flexible pad that offer resistance, there is a flexible pad is there, there is some effect on the ground shaking will be transferred to the building. So, flexible pads are base isolators, whereas the structures protected by the means of devices are called base isolated buildings. The main feature of the base isolated technology is that it introduces flexibility in the structure. So, in flexible structures, the structure will not move, the ground will move. So, that is very important thing. That is, for example, a small building, our house, etc. built at rigid only. But when it comes to a large, heavy building, then the forces will be very high. There we will be introducing these type of isolators. That such buildings are known as flexible structures. So, this is an example. So, this is an example of a building which is having an isolator. This is an example where it is rigidly fixed. Here you can see the vibration is very high. Okay, this will result in the destruction, but here the whole parts of the building will be moving in a same way. Okay. The isolators are of some types are there. This is anyway not that much given in your syllabus, but anyway you need to have an idea about this. There are two types: elastomeric isolators and sliding isolators. Elastomeric means we will be having some fabric like material will be there, some spring like arrangement. Sliding isolators means that is of some other types, some external force, external methods will be given. So, elastomeric isolators, they are formed by horizontal layers of natural or synthetic rubber in thin layers between steel plates, bonded by steel plates. The steel plates prevent the rubber layers from bulging, and so the bearing is able to support heavy loads. Plain elastomeric bearing provides flexibility but no significant damping and will move under service loads. Methods used to overcome these defects include, this is an example. Lead cross in the bearing, specially formulated elastomers with a high damping and stiffness for small strains and other devices are apparent. Then this elastomeric bearing, you just read this. There are different types are there. Lead bearing, lead rubber bearing. Then it is isolated system based on sliding. That is, we will be providing this is a system. A system is being arranged. Like this, and pendulum arrangement. That is a friction pendulum is being arranged. So that is friction pendulum. Okay. Now that is isolators can be of this elastomeric isolators and sliding isolators. These are mechanisms. Here it is a material. So based on that, there are different types are there. You just read it. You just have an idea about this. That is when you are working as an engineer, practical engineer and all, it will be useful. So that is the reason I have given. Then which are the locations of isolators? The requirement of installation of base isolation in a building be able to move horizontally usually be at least 100 mm. The most common configuration is to install a diaphragm immediately above the isolator. If the building has basement, then the options are to install isolators at the top, bottom or mid height of the building. That is, these are the locations. That is, if a building, here I can find a isolator. Then this another form is there. At the base of the column I can fix the isolators, or at the middle of a story I can fix the isolators. So there are different locations. That is based on our topography of the land, etc., or what are the cost, what is the load coming, etc. We are having different locations. Then some applications of isolators. So this is a real example. That is a Burj hospital building built with base isolator after original district building at Burj, after the collapse, Burj earthquake. That was very much. So here it's a basement column is there, then we are providing an isolator. Okay. The base isolation provides an alternative to conventional fixed based. Base isolation minimizes the need of strengthening the structure by adding shear walls, then frames, bracings, etc. Base isolation has the effect of reducing the earthquake. So here another term is shear wall. That is, shear wall means the concrete wall that is mainly located at around the, for example, around the wall for the lift. We are having the lift, right? That wall is mainly concrete wall. Concrete wall means we will be having reinforcement. Mainly the wall is made up of bricks. Instead of that, if a concrete wall is used, that is known as shear wall. So importance of a shear wall is that it will attract the lateral forces to the building, and thus it will reduce the effect of earthquake. So that is important. Now the seismic base isolation method have provided to a reliable method of earthquake. The success of this method is largely attributed to the development of isolation devices. Then efforts are being required to find out the solutions for the near to prevent the earthquake, etc. So here so far I discussed about base isolation. The thing is that you need to have an idea about these things. What are the materials being used? What is the location, etc. Now next, the main topic coming into as per our syllabus is the force vibration due to so you can see this is a syllabus. So here, response of undamped and damped STF system to support motion. From that coming, it is vibration isolation. Vibration isolation is a two type: force and displacement, and the term transversality. So these are the things which we need to study. So here so now let us look into this term, that is force vibration due to support motion. What is support motion? That is earthquake. Now due to support motion, so before seeing these equations and all, let us take into another problem, that is so due to support motion. There are cases where foundation or a support of a structure is subject to time varying motion. So ground motion of earthquake or other excitations as explosions or dynamic action of machinery causes the support motion. They are considered to be considered in the analysis of dynamic response of structures. So support motion means the support of an oscillatory modeling the structure is subject to harmonic motion. That is, the motion will be in the terms of, that is, if Z is a displacement, then the support motion Zt is equal to Z0 sine omega t, where Z0 is the maximum amplitude and its omega dash et is the frequency of the motion. The motion means there will be a frequency. So first this is, we are considering the general equation. What is the equation? We know that mx double dot plus cx dot plus kx is equal to 0. This is our equation. Is equal to 0. So here in support motion there is no force. That's the reason why. Now here what is the change? The change is that here there is a motion. That is, the acceleration will be there, but the displacement will be, instead of x, it will be x minus z. Then x dot, it will be x dot minus z dot. So that will be the change. So this is our equation. That is mx double dot plus c into x dot minus z dot plus k into x minus z is equal to 0. Now here instead of z, we know that it is this term. So z is equal to z0 sine omega t. Therefore I can just write I can take the derivative. So here I can substitute, instead of z I am substituting z dot sine omega t, and z dot what it will be, z0 omega t omega dash cos omega t. Okay, this will be z0. Okay, so this will be my term. Okay, so here it will be z0, sorry, it will be z0. So you can substitute, you can see that here I am having two terms, that is mx double dot plus cx dot plus kx is equal to, I am taking these negative terms to the other side. So this will be my solution. z0 k sine omega dash t plus c omega dash cos omega t. Now I can substitute these terms, that is putting, instead of this term I am introducing a new term, that is here I am having two terms are there. So I am converting this into f0 sine omega plus alpha, sine dash omega plus alpha is the, it will be the phase. Okay, therefore I am substituting here, instead of this I am substituting putting f0 sine omega t plus alpha. So here I can substitute, that will be equal to this term. So from that I can find out the constants, that is instead of the coefficients of cos omega dash t and sine omega dash t. So here the instead of f sine omega t plus alpha, so that is equal to z0 into k sine omega dash t plus c cos omega. So what we have done here, just start once again I will be saying, that is here now we are going to study about this due to support motion. Support motion means there is a displacement. So vibration can be of two types, one is due to displacement, other is due to force. So now we are going to find out the displacement. So displacement here, it is a, we are taking it as a harmonic motion, it will be like that. So that displacement is equal to z0 sine omega dash t. Okay, that is a displacement. So we know that the equation, this is the equations. So here instead of x, it will be x minus z, or x dot will be x minus z. So here you can see, so this is the our diagonal. So here one thing you need to understand, x double dot, it will not be x double dot minus z, because it is a, that is due to the force only. Force is always due to acceleration, that motion only. So that is the reason why here we are taking x double dot. So I am substituting my different values here. I will be getting an equation like this, okay, by rearranging. Now this term I am considering it as a new term, that is f0 sine omega t plus alpha. Okay, I am just putting substituting like this. So from this I am going to find out what is f0. So by after substitution you can see here I will be getting terms of that is sine omega dash t and cos omega. So I am just substituting the coefficients of sine omega t. What is sine omega t coefficient here? f0 cos alpha is equal to, here what it is, k z0. Here f0 sine alpha, that is equal to c z0 omega dash. So I am now taking I am now dividing these two. So after division I will be getting a term that is equal to tan alpha. So tan alpha is equal to c z0 by k z0. z0 cancels. Here it will be, so c double omega dash by k. But we know that what is c by k, or I can write, so here you can see it will be c by k omega dash. Okay, c by k omega dash. Now here I can write, so here c by k it is equal to 2 theta by omega. Okay, 2 theta by omega. This we already have derived as c by k is equal to 2 theta by omega. So now I can write what is theta. Theta is equal to omega dash, that one. Now instead of omega, so I will be getting like this, 2 theta omega by omega, top it low. So omega by omega, that it is a new ratio. I am taking it as r, that is ratio of the applied frequency to the natural frequency r. So here you can see, so I am having f0. So I am squaring these terms and adding, that is f0 cos square sine square omega t plus co, that is equal to c square. These two terms, these two equations I am adding. So by substitution, what is sine square alpha plus cos square alpha, this will be equal to 1. Therefore I will be getting f0 is equal to z0 into k. f0 is equal to z0 into k root of 1 minus 1 plus 2 r theta square. So here you can see this c by k, again it is 2 theta by omega. So similarly I can write 2 r theta the whole square. R is a ratio of omega dash by omega, that is applied frequency by natural frequency, that is a omega ratio. Okay, now here, so this you can see here, that is, this is r which I am writing here. Instead of r you can write beta also. Both the terms are same only, so no need to have a doubt in that. It is the same ratio only. Okay, so here that is, here you can write beta theta, like that also you can write same. So this, in this note it is written r, so instead of that I am just using beta also you can use, same equation only. So this equation is changed to this one, that is, this was our starting equation and that have changed to, this equation have been changed to this main equation. Is the new equation is mx double dot plus cx dot plus ks is equal to f0 sine omega dash t plus alpha, where alpha, it is now, it is written here. From here you can find out what is alpha. So what has happened here, a ground motion is being converted into a motion. This is a harmonic motion. This we studied in our harmonic that loading, that video you can just refer. So the same thing, so it is here, from here only it started, that is this equation. This we have studied, mx double dot c dot is equal to p0 sine omega. It is same equation. Now it is the same thing. So we converted a ground motion to a forced motion. Then it will be easier for us to find out the values. Now considering there are two stages are there for steady state response. So I'm just referring that also, then it will be having an idea. So this is our amplitude which we are getting. The same thing we are writing here, p, that is, you can write here p0 by k root of 1 minus beta square into 2 theta beta. Now here the same thing, that is, here you can see the amplitude, steady state amplitude will be, instead of p0 it is f0 by k sine omega t plus alpha minus beta. So this beta, it will be the phase angle. Okay, so you can see this, so Zp, that is a steady state response, is equal to Z0 into, in f0 we have found out as like this, same I am substituting here. So I will be getting an equation. Now I am taking Z0 to here, Zp by Z0 is equal to root of 1 plus 2 r theta divided by 1 plus 1 minus x square the whole square, this term, into sine omega dash t plus alpha minus beta. So this expression for the relative transmission of support motion, this is the expression for the equation. Now the degree of the relative isolation, this term, that is a new term is been introduced, it is called the transmissibility, that is defined as a ratio of the amplitude of the oscillator to the amplitude of the oscillator to the main amplitude Z0, that is a motion of the support. So this is the important term, transmissibility. So transmissibility is equal to Z by Z0. So that is the term. So this term is represented this is an important term, you need to have an idea. So here transmissibility ratio. So this vibration isolation we started. So the vibration can be of two types, forced vibration, force can be transferred, another it is displacement. So this is the transmissibility ratio of a displacement. Same equation will be for the other also. Now here I can apply some terms, that is if R is R is beta, if beta is equal to 0, and if damping ratio, okay, this is the damping ratio theta, that is C, this is equal to C by Cc. Okay, so why here I think you might have a doubt here also, but why I have written like this, that is what is theta? C by Cc. Okay, then what is Cc? 2m omega. Okay, so Cc, so here C by Cc is there, so instead of that is theta is equal to C by Cc, but Cc is C by 2m omega. Okay, now instead of m I am changing, here I am not having any m term, so m is equal to, what is omega? Omega is equal to root of k by m. So if I am taking omega square is equal to k by m, so m is equal to omega square by k. Okay, it will be so I can write m is equal to k by omega square. So here instead of m I am writing k by omega square, so omega will cancel. So how can I write this? Omega will be going to the numerator. So here I am having C, here k is there. Okay, k is there, so C by k is equal to what will be that is 2 theta by omega. So that is a term, that is how this is been written. Okay, so we started so here this ratio, that is known as transmissibility ratio, and here we are having many conditions, that is where if R is equal to 0, if R is equal to 0, TR is equal to 1. If in this R is equal to 0, that is if the ratio is equal, then if R is equal to root 2, then TR is again equal to 1. Then if R is equal to alpha, then TR is equal to 0. So likewise for each values of R and theta, the transmissibility will be varying. So just a table is there, you need to have just an idea only, and if I am plotting these terms, I will be getting a variation like this. Okay, so here you can see at R is equal to root 2, the term, that is this term will be 1. So that is a root 2, it is an important condition. Okay, so this term here you need to understand this equation, transmissibility. Okay, and with this a small problem is given here, direct equation only. Here you are given R is equal to omega dash by omega. So here in a frame is subjected to a sinusoidal ground motion. The ground motion is given. That is how it is given. Zt is equal to 0.5 sine 15t. So that means 0.5 it is the Z0, and this 15 it is the omega dash. Okay, then it is given, determine the transmissibility ratio, maximum shear force and maximum stress. So here you can see omega is equal to k, it is the frame in 2.15. so the equation, it was the k, it is given in the question, k is 26 something, then from omega you can find it, omega will be also given in the question. So omega dash is equal to 15. So R is equal to omega dash by omega, so we can find out R. From that I can find out what is the transmissibility ratio. Okay, then after that we can find out the stresses and all. So I will be explaining more on this in the next video. Video I will be explaining more. So just understand, so what is upward motion and all, one more detailed explanation will be given. So as of now I am ending this video. With that is we started with the half sine wave, then we discussed on vibration isolation. So regarding this vibration isolation and regarding the support motion, so we need to know some more terms. So I will give some detailed explanation in the next video regarding the transmissibility and all that. Then it will be clear to you. So that's all for this video. Thank you.